Geldi mi acaba?
Evet hocam, sunumumuz yansıdı şu an ekrana.
Tamamdır. Um, Hello, dear ladies and gentlemen. My name is ZAUR RASULOV, and I'm fourth year bachelor student of mathematical engineering at Yıldız Technical University in Istanbul, Turkey. Today, I would like to present our project that I, together with my supervisor Fatma Aydın, have been working on for 1 year. Our project is related to fixed point theory and especially fixed point iteration. Together with my supervisor, we developed a new iteration method for finding the approximate solutions of third-order boundary value problems by embedding Green's function. And let me start with a little bit prehistory of the method. So, firstly, fixed point iteration is an essential tool for linear and nonlinear problems. The main justification for us to think like that is the understanding of the problems, and we know that analytical solutions of the majority of linear and nonlinear problems are either found with difficulties or it is even impossible to find them. And that is why, since the very history, the many scientists have developed different numerical solutions for finding good results. And fixed point iteration method is one of these methods. The method itself was introduced by Liouville in 1837, after whom in 1890, Émile Picard, a French scientist, introduced a new algorithm which was developed for finding the solutions of initial value problems. In other words, IVPs. After approximately 60 years, another American scientist, Robert Mann, in 1953, modified the method by Picard by simply applying a new parametric sequence called alpha, which was defined in the interval 0 and 1. However, despite of all of the things, Mann showed that his method worked better compared to Picard's method for initial value problems. Since the last decade, the interest of the majority of scientists in the field of numerical analysis and especially fixed point iteration has been increased considerably. And for example, in 2004, and Seife, two scientists developed a new algorithm which was related to finding the solutions of boundary value problems. And there they showed the main point is that Green's function, which was defined by Green, can be used for boundary value problems, and they satisfy the conditions of different boundary values. And that is why later, after about 1 year, Mariam Abu Shamala and others defined a new method called Picard-Green's method, which was used especially for finding the solutions of boundary value problems. Third-order boundary value problems are very important in both pure and applied mathematics. At the same time, they are considerably used in pure and applied physics, for example, in finding the solutions of equilibrium problems. At the same time, third-order BVPs are used for finding the solutions of engineering techniques, control theory and optimization, fluid dynamics, air elasticity, sandwich beam analysis, beam deflection theory, and other fields therein. Let me define our method. The method itself is called Kohn-Green's iterative method and was firstly defined by Femin Ali in 2019. For second-order boundary value problems. The method itself is defined in this way, and here we can see that we have two different equations, where our initial point called P0 is an element of Y, and Y here is a non-empty convex subset of Banach space X. Also, P is a mapping on a non-empty convex subset Y of a Banach space X, and finally Rn is a parametric sequence in 0 and 1. Moreover, I'd like to say that congruence method is actually the composition of two different methods. First is Picard-Green's and second is Mann-Green's methods. I'm sorry. And let us define our problem. As was mentioned before, the problem is related to third-order boundary value problems. Our problem will be defined in this way, where the right-hand side, the part with f, can be both linear and non-linear, and our boundary conditions are given as following. However, for the existence of this type of problem, we should satisfy three conditions. The first condition is that f t x y z should be continuous function in 0 and 1. Here x, y, and z are ut, the first derivative of u with respect to t, and the second derivative of u with respect to t, respectively. Also, the function itself and its partial derivatives should be again bounded. And finally, our function should be strictly positive on 0 and 1 times r cubed, where 0 and 1 are representing the values of t and x, y, z are representing the values of r. So it means that x, y, z can be real numbers. Of course, in case of defining congruence method, we should define, of course, Green's function as well. First, let us define our problem in this way, where LU is actually our operator, Green's function's operator. And after applying all the conditions of Green's function and applying all the boundary conditions, we will be able to define our Green's function in this way, where a1, a2, b1, b2, and c1, c2 can be both constant and variable coefficients. On the other hand, u1, u2, and u3 are our linear combinations, and the Green's function itself is defined in the interval of a and b. After that, we can define our Green's function as this, where up, which is a particular solution of our problem, equals to the integral from a to b Green's function multiplying to the right-hand side of this function, and the integral should be taken with respect to s. And let me define our congruence iteration method more detailedly. For defining our method, first let us consider third-order boundary value problem in this way, where LU is our linear function, NU is non-linear function, and F can be both linear and non-linear functions. MUP, which is our integral operator, which will be used in the further applications, equals to this. And for the future, for the following steps, we will substitute UP with U just for easiness. And after defining our integral operator in the general form of congruence method, we will be able to obtain this result. Here we can see that Qn equals to Pn plus Rn times integral from a to b, Green's function, times our problem. And Pn plus 1 equals to Qn plus the integral from a to b, Green's functions, times our problem, and all integrals should be taken with respect to ds. And also here our initial solution, initial point P0 should be the solution of the homogeneous solution of the highest order of the problem only. This means that we will find the homogeneous solution of the third order derivative only. And after that, let me define our convergence. For defining the convergence, let us consider the third order boundary value problem in this case, with which subjects to the boundary conditions provided in as following. And after applying all the conditions and all the boundary conditions of our problem, we can find our Green's function as is presented on the graph, as presented on the presentation. However, for some problems, to show the convergence of our problem, we should find the adjoint of Green's function, which is defined in this way. And continuing on with convergence, let us define our integral operator as is presented. And here our integral operator will be equal to TU. Applying our contraction mapping such as presented on the screen, like TU minus TV, and we are taking the norms of it, we will be able to define our problem in this way. And after applying all the algebraic operations and taking the mean value theory, we can find that our TU minus TV will be equal than delta, will be less than delta times U minus V, where delta equals to this part only. And our delta will be our convergence rate. So we can say that our convergence rate equals to 1 over 20 times square root of 3 times supremum of the partial derivative of f with respect to u. And here is all for our theoretical part. And now I would like to present two different nonlinear examples. And let me start with the first example. Let us consider this type of third order boundary value problem. As was mentioned before, this is nonlinear third order BVP, which subjects to the boundary conditions and this. Also, it's worth to mention that our problem does not have any analytical solutions. That's why we will compare our results with the results obtained by different numerical solutions. The Green's function and the adjoint of the Green's function will be defined in this way, because only in this condition our problem will converge to 0. And let me define the first equation of our problem as Qn, which equals to this. And here, and for the further solutions, we will use 0.99 for our parametric sequence, which should be in between 0 and 1. And our Qn actually equals to the integral from 0 to t, Green's function first equation times our problem, plus the integral from t to 1, Green's function second equation, times our problem. And the integrals should be taken with respect to s again. And defining our Pn plus 1 in this way, we can say that our initial point P0 equals to 0, and the method for finding this was mentioned earlier. And here I would like to present some results. So here we can see that our results are given for different values of t from 0 to 0.4. And here we show the numerical solutions found by Green's iterative method. And here we represent the errors for two different methods. The errors are found in this way because our exact solution is not defined. And according to our table, we can see that Green's results, the errors obtained by Green's method, converge to 0 faster compared to Picard-Green's method. For example, here we can see the exponential 10 times minus 13, while here we can see 10 times 2 minus 8. And for better representation, I can show you the graph of relative errors of our example. And by applying the formula of relative errors defined in this way, we can see from the graph where red line is our Green's method and blue line is our Picard-Green's method, we can see that Green's method approached to 0 much faster than Picard-Green's method. Here was the end of the first example, and now let me represent the second example. The second example itself is also a nonlinear problem, and which subject to the boundary conditions given as this. And here we can find our exact solution given as this: t squared times 3 over 2 minus t. The adjoint of Green's function will be defined in this way, and defining our Qn, which is defined in this way, and our Pn plus 1, the next iteration, will be defined in this way. Here Rn is our parametric sequence, which also can be 0.99, and all this parametric sequence can be either found arbitrarily or by finding the residual errors. And now let me show the maximum errors. We have showed the maximum errors for 3 different iteration numbers, for example, for 30, 40, and 50. And here we can see that for the 30th iteration, we have 10 to the minus 45. For 40s, we have 10 to the minus 59. And for the 50s, we have 10 to the minus 74, which shows us the very good results of our method. And here I would like to show several errors, absolute errors, which can be found by finding the difference between the approximate solutions and exact solutions. Here we compared 3 different methods: congruence, Picard-Green's, and Mann-Green's methods. And we can see that comparing all of these methods, we can see that congruence method again approach to 0 much faster. We have used several references, and for example, we have used a reference like Emily Picard's article, Robert Mann's article, and the references therein. Thanks for listening.